Awesome, yes.
So, we're testing out something new, which is recording with my phone over there, which means that my internet addiction will go like completely horribly over the next about an hour and a half. But I do have my iPad that I'm going to try to install Twitter and everything else on in the next 20 minutes or something, so I can actually continue to have this addiction. So hello everyone, thank you so much for coming. Thank you for taking your time away from the dear presidential Republican debates that's happening basically right now. So I know you all care more about HTML5 and JavaScript than any particular US politics. So I'm John Paul. I recently, in order to introduce myself more efficiently, because I typically don't do that here at all, but I do that in other contexts, I actually put myself up on NPM, so that you can NPM install John K. Paul. So in case you want to know anything about me, or the meetup, or my job or otherwise, please go NPM install John K. Paul and you will find out everything.
Is there a CLI?
There is a CLI, but all it does is print out, there is a CLI.
John K. Paul --streams.
Yes, John K. Paul --stream or something. --help will do the same thing. It's great. I covered every base. It's unit testing. That's how we roll. So first of all, thank you for coming. I'm very excited to see you all. Second, so in case some of you are surprised at how this whole RCP situation worked, first of all, I want to apologize for having to cancel the last meetup. The last meetup in October, some of the people that you are going to hear tonight were scheduled for that time, and this is something that was basically completely my fault, and I will explain why, in that I am actually getting married in approximately 21 days. Thank you, which means that I have so much work to do. It is unbelievable. The lists that I have going in Trello are more longer and complicated and completely ununit testable. I'm basically not like any software project I've ever done. I feel like it's actually a lot easier to have a software project than it is to have a real life. The meetup doesn't count, because the meetup is a real life event. But if anything happens, I can just cancel it like I just did. Move it to this one, it's okay, no one's going to have a problem with it. For a wedding, you can't really do that without even flying. Lots of other problems.
Don't try that.
Yes. Sure. So also in case any of you have been emailing me, other than trying to get into the RSVP for this meetup, which I've gotten like 150 emails today, which I'm very grateful for, I've not responded to basically anything. And I've canceled the last meetup and done lots of things in order to make that happen. But so December will be holiday party or something interesting that I will be figuring out. Starting in January, we will again start up the regular cadence for NYCHTML5. So I'm excited for potentially having something really fun and really great for us to all socialize together in December. I'll figure that out and you will get emails. I'm assuming you're all on the RSVP list anyway, because you are here tonight. So I will start off just by getting started. Eventually I'll be talking about other random things, potentially keeping you up to date on the state of Donald Trump in the Republican debate. Let's see how that goes. If there is anything interesting, I will let you know. I want to first start off with David Valdman talking about 60 frames per second and more. I think the reason that the meetup was so popular was the particular title that happened to be his talk. So I'm very excited.
Thanks. If I can live up to that excitement. Oh, I need to plug in, right?
Yes.
All right, looks good. Sweet. So the original title was Functional Layout, updating the DOM at 60 frames per second, but we can just concentrate on the 60 frames per second part. So I'm Dave. Just a little bit about me, I actually just moved back to New York. I'm moving to my place in a couple days. I did this brief stint in San Francisco for a few years, working at a company called Famous. How many people have heard of this company? Awesome.
It's famous, you might say.
Quasi-famous. No, it's great when people haven't heard of it. I'm like, damn it. If you haven't, maybe you've seen this demo a long time ago. We made this a few years ago where you have this like 3D infinite scroll view that you can like zoom in and look at all this 3D content, or enter into a sphere or something like that. Work it around. So this generated a lot of buzz, and that was like kind of the birth of Famous. But recently, Famous had a death. So that came out a few days ago. I actually left the company about a year ago. That was my stint in San Francisco. But I've been working on kind of related problems since then. For the last year, I've just been traveling around and quietly coding in Southeast Asia. Yeah, so I also have like no tech friends in New York. I'm literally just moving back here, and there was no tech scene when I left. So let's all hang out and have a beer afterwards. Awesome.
That's the plan.
Great. Okay, so updating the DOM to 60 frames per second. So the first thing to ask ourselves is, what updates at 60 frames per second? And it's not things that look like this. This is just some handlebars template, some book item just I ripped off the handlebars website. We're not trying to update content at all. All of the kind of MVC libraries out there, they're kind of all doing, they have some kind of opinion on data binding and updating content from some kind of model. But that's not the kind of stuff that changes at 60 frames per second. You don't change book titles that quickly, unless you read really fast. So what does update? It's all things that have to do with user interfaces. Animation, scrolling, dragging, gestures, and resizing for responsive design. These are all things that have to do with layout, so things moving around on the screen. Sizes, positions, orientations, things like that. So when we're talking about updating the DOM to 60 frames per second, it's important to make the distinction that we're not talking about content, we're only talking about presentation. And so I think it's kind of an anti-pattern to try to update the presentation of a document by having some kind of model representation and updating the view. Maybe you'll have exposition of some modal that's on the screen, and you want to move that modal. But that shouldn't be inside of the model of whatever modal you have. That should be something separate. This is a different kind of pipeline that we're thinking about. We're not doing data binding from model to a view. We're doing a different kind of data binding. So in this slide, I make the distinction between content and presentation. HTML is always about content, and CSS is supposed to be about presentation. So you might be thinking that, well, maybe the key to all of this is to create some really super badass CSS framework. So I'm going to try to make a case that that's actually not what I'm trying to do. If we think that these are the three pillars of the web, where does presentation and layout belong? And I think it's, most people would kind of say it's on the left to HTML and CSS. Because HTML has its opinion about layout. It has block elements and inline elements. Block elements place underneath each other, and inline elements placed to the side of one another. And CSS has tons of opinion about layout in all of the CSS properties. We're not talking about things like color or background image or something, but top, left, position, all of these that are inside of CSS. So we have layout primitives inside of two different things, HTML and CSS. But JavaScript over there is kind of lonely out to the side. And how I would describe how HTML and CSS view layout is thusly. So if your website was just HTML, nothing ever moves on your website. It's pretty much just static. If your website has a bunch of CSS, you can always trigger a class to queue some kind of animation or set a style property, move something around. But these things are always kind of binary operations. When you add a class to queue an animation, you're just toggling a switch. You're turning something on or off, and then something might animate on your screen. It's great for some kind of, something is entering in or exiting from the DOM. You might want to animate that in, animate the opacity, give it a transition or something. But these are still binary, just flipping a switch. And if we want to do something that's continuous, we have to do something with JavaScript. So even the simplest thing in user interfaces, which is dragging a div by your finger, it's impossible to do that just with CSS and HTML alone. You need to have some kind of JavaScript going on that's tracking the finger and updating CSS accordingly. So I've been working on a framework on my own. It was actually originally a fork of Famous, but like the ship of Theseus, there are now 900 commits on top of it, so I pretty much gutted everything. So it's called Samsara. That's where you can find it. And Samsara has a few principles. And these principles are a little bit weird, honestly. The first principle is that user input can be thought of as a stream. So streams are all about continuous data flow. Things that are changing at 60 frames per second, you can really abstract that away as thinking that it just changes continuously, and you have just this stream of data that's going on. And eventually that stream of data is going to hit the DOM and update something at 60 frames per second. But user input isn't normally thought of as a stream, but that is a stream. That's exactly what a stream is. So it's something that emits events with data, and you think of those events as happening continuously. And really a stream is nothing more than some kind of an event emitter where we've just standardized on the names of the events that it sends. So on Node, the standardization is a data event and an end event. But it's just, there's nothing to it. It's really just an event emitter where we've just made some kind of opinion on the kinds of events that it emits. So all of these user input things like scrolling, resizing, they were always just streams. But you never think about that. And the reason why you never think about that is because there's no way to pipe them anywhere. So streams are really useful when you can take one stream of data, transform it into another stream of data, transform and then end with something that you actually wanted. But you can't pipe the mouse input that you're getting, or pipe the touch input, or something like that. But what if we had an API to enable us to do that? So this is the beginning of having the DOM updated at 60 frames per second. You first have to capture user input at 60 frames per second, and then do things with it. So you have some widget, and it can subscribe to the mouse. Or you have a gesture recognizer, and you can subscribe to the touch input, so that when a user makes a little circle, it could say, it can emit its own event, circle. Or maybe it's a gesture like swipe left or swipe right or something like that. But once you have this kind of streaming API, you can build up higher level streams out of lower level streams. So maybe calculate the velocity on the scroll, or pinch the zoom by tracking 2 fingers. You can keep building up these higher level streams from lower level ones. So the first thing I want to do is ingrain in people's minds that user input can be thought of as a stream. And now there's the second principle, which is that layout can be thought of as a stream. And this is the one that's also pretty unusual. You don't really think about streams on the front end like this. But let me give you an example. So that bit.ly address is also, you can go there on your mobile phones, and honestly this is a much better mobile phone demonstration than it is a web demonstration. That the second to last letter is a capital I. But what I'll do here, where's my mouse, is I'll drag this from left to right. And there's many things that are happening here, okay? One is my user interaction and the way that the layout is updating is happening in lockstep. There's nothing binary happening. As I'm dragging, the user interface is changing. But more than that, so many things are happening in parallel. And that's the huge advantage of having these streams, is what's actually happening here is the nav bar is listening to how the blue thing is traveling. So is that red sidebar. And what's happening here is that first the user input goes to the blue guy. The blue guy emits 0s to 1s as the progression is, as I'm dragging the finger. At some point it clamps the mouse input. It doesn't care that I keep dragging, so it's only emitting 1s. And the opacity and the translations and the rotations that are happening all throughout this app are just literally subscribing to the layout. Everything happens at 60 frames per second. You can click on the back button and the messages button or wherever and have that kind of binary thing that you expect from CSS. But what I'm trying to do is build something so that everything is happening in lockstep. And that's the kind of things that we see in the native world when you press the back button in your text messaging app on iOS or on Android. 10 different animations are happening all at once. Everything is shifting. It's not jarring. It's all done. It's all just done really well. Not to make some kind of jarring experience for you, but just to make this really playful experience of swiping between screens in your application. Okay, so that's what I mean by layout being a stream, and it starts from user input. So the question is, how do we build something like this? So this goes into kind of the architecture of, well, I'll get to that in a second. So there's a little bit more of a history, what browsers do when you're not looking. So this is an old slide that I got from the internet several years ago. I still think the web works something like this. Now there's Blink also, in addition to WebKit. But browsers take this pipeline where you don't have to understand all the little nodes here, but they take the DOM and they take your styles and they combine them into something that's called a render tree. And all that is the positions, heights, and widths of everything inside of your document. All they care about is rectangles. They don't care about the content. That'll be done later in the pipeline where they paint your actual content. But all they care about is the placement of things, the layout of things. And the point of this framework is to take that part out of the browser and give it to the developer so that you're actually the one in control of all these boxes moving around on the screen. And the way to do that is to create our own little render tree and to position absolute everything in CSS. So we take it out of the browser pipeline and give you manual control of how everything happens, how everything moves. The render tree can just be thought of as a bunch of these nodes that just have layout information. So you give them some kind of information. I want A to be translated right 100 pixels and down 200 pixels, and then B to be translated 50 pixels to the right. And then at the bottom of these things are actual things in your DOM element. And the render tree will collapse them down into where they actually appear on the screen. So it will combine A and B for the case on the left. And then maybe C and D have some other fancy properties. It doesn't just have to be translations. It could be rotations, scales, skews, whatever you want. Or you can even be fancier. Let's define a size and an alignment relative to that size so that the guy on the right, he'll have 50% of the size of C, and 50% of the width and the height of C, and then also the translate on A, and that'll collapse down into this style property. So 50 plus 100, and then 25 plus 200 are those numbers. So you can take this idea to its logical conclusion. Let's build an entire tree inside of JavaScript. But the actual HTML of this entire page will be totally flat. So if I go over here, oh, whoops. Oh, I wasn't supposed to click, sorry. ruin the fun. Here, let's make this bigger. So if you were to do this in CSS, you would have 8 layers. This is a fractal tree. There's 255 elements on the screen. Here they all are, but they're all at the exact same level of HTML. Let's start at the first one so you can see it. There's number 1, smiley face. There's number 2, 3, etc. But this entire tree is represented in JavaScript, and then it's just exported to HTML in a flat structure. And here it is animating. And you see what's happening is all these little matrix transforms are updating the DOM. I'm actually surprised this isn't blowing up my computer because it's 255 guys right here. So that's, hopefully that gives you a sense of what we're doing. We're building this whole tree representation in JavaScript, and we're just positioning, before it touches the DOM, we're positioning everything. But I've been talking about streams this whole time, this concept of streams. So what if the render tree wasn't actually a tree where you have a node and children nodes, an array of children? What if it was just one big stream? So what this means is that every single one of your nodes contains some kind of data, translates, skews, scales, whatever it is. And the children listen to their parents. So every time you nest, the child is listening to its parents. When its parent changes, those changes trickle down to its children. And at every single step, they compose. So 3D transforms will multiply. That's how their matrices multiply. Opacities will also multiply in a scalar way. Opacity of 0.5 and 0.5 will give you 0.25 after you nest them. But then all the other things like size and align, they just combine every step of the way as you trickle down this tree until you get to the DOM. All of these nodes are composing. It's called a stream transform, just how streams can change. And at the very end, they end in the DOM in opacity, transform, or sizes. And opacity and transform are both hardware accelerated, so that's all done on the GPU. Size isn't, but you can't really talk about layout without talking about size. So that's the architecture. And the third principle of Samsara is that rendering is a stream. So the entire pipeline from the user input to the layout primitives themselves to actually how they're rendered, everything is one giant stream. Because that's the language of 60 frames per second. So Doug McElroy once said, write programs to handle text streams because that's the universal interface. I don't know if you've heard that quote. Who's here has heard that quote? No? All right, some people? Yeah. That's done because I/O is always kind of text intensive. And when you're piping things in bash, it's just text streams that are going from one bash command into another bash command. And what I'd like people to do, and I should also add that in Node, everything is a stream because you're doing I/O. And I/O is very stream-based because Unix the file system is one big stream, how it's sending text streams around. So what I'd like people to do is to think about layout on the front end as being a stream, especially when you're talking about animation, anything that happens at 60 FPS. So me, speaker at HTML5, write layout to handle JSON streams because that could be a universal interface. And really, that should be the interface for animation. So let me give you some more demos to illustrate what I'm talking about. This is actually the logo for Samsara. This is all DOM also. It's this crazy spiral. So the Samsara wheel is a six-sided wheel or whatever from Hinduism and Buddhism. And it's supposed to be the idea of continual rebirth, of death, of birth, life, death, and then rebirth. So that's how I think about animation in a way. Can I resize this? I have to go out to full screen. But here's what's cool. I mean, as this thing is changing, as I'm resizing the screen, the resize event from the browser is a stream that's getting reinterpreted through all of the primitives that are all like kind of defined proportionally to scale the actual guy. And this is happening many levels deep. This is kind of a trick that I kind of came across on the internet. Unwell known of how to make a wedge in DOM. I don't know. It's there's one container element that is giving a skew, and then there's a circle underneath that has the anti-skew in order to still be a circle. But so the size is actually flowing through the container element and then through into the actual surface in order to resize. I mean, just try doing that in CSS. It would be difficult. Okay, so there's that demo. Here's responsive design. Okay, so we're gonna move this guy around. This is also changing the size, and this is all done in JavaScript. There's no CSS happening here. And as I resize the window too, it doesn't matter. Everything's defined proportionally, so it doesn't matter if I'm resizing this guy or the window itself. And here's another bit of layout. Here we have this double parallax thing that's going on. Like as the cat images are moving up and down, some kind of scroll view, a little bit of one is being removed and a little bit of another is being added. Some scroll view that goes up and down. And what's actually happening here is the way that this works is, okay, well my mouse's move events are being the stream that's actually translating this guy. But each individual image is also moving up and down, and that's listening to the output of the scroll views, which is emitting events that go between 0 to 1, saying how much has it progressed, and it's the cat image is moving up and down relative to that. So from one stream, my mouse, to the stream of the scroll view, to the stream of the actual images that are moving up and down. And you can click down here and move around also. What's this one? Oh, and then you can just, like, this is all 3D and crazy, so why not have a weird scroll view that is this weird accordion guy that instead, this was just like me just playing around. I don't know, this has no practical purpose whatsoever. But it's hella fun just to do this. So the whole point is to be creative. Like, I don't think that before we had a language for talking about not just to do animation, but how to have all this kind of coordinated animation. There are so many libraries out there that what they do is they take a single DOM element and then they allow you to animate some CSS property on that, change its opacity, change its exposition, whatever. But the point of this is not to animate just one element at a time. It's to coordinate the animation of tons of elements that are on your screen. I want you to feel like you're a conductor of an orchestra, not a player of a single instrument. And those are the kinds of experiences that we see in the native world. Many things harmonizing, happening together, not just something going in or out. And I think the reason why we don't have this is because we don't have the right language to think about, well, could I take this CSS class and pipe it to this other CSS class? Like, you can't do that in CSS. You can't coordinate different elements together, make a link between them. So, but you can in JavaScript with a stream-like language. How am I doing on time?
4 minutes.
Sweet, because that's the end. So the whole point is to have more, with ease of expression comes experimentation. Like to give people a language to think about doing this in terms of streams so that it can be more creative. And also not have to worry about performance, because all this stuff is hardware accelerated and hella fast. You just saw 255 elements moving around the screen. There's been so many of these. What I want to do is I want to encourage people to make all these kind of weird UI things. So there's drag and drop and inertial scroll. These are all things that have been invented. You know, we didn't. Now, if you're coming to the development world, you're bored into it. But so many of these user interactions haven't been created yet. And the question is, like, can you just play around and make your own for your own app, and do it on the web and not have to do it in native? So that's that. That's where the library is and where the GitHub is. It's MIT licensed. And I'm happy to take questions. Yeah.
So, I mean, I haven't taken a look deeply into the API, but from the quick example that I saw, it looks like a publisher-subscriber pattern. How is this any different than that? Or have you decided maybe, I'm sure there's probably some argument on the forum to change the function names to be more like pipe or stream or something like that to be more in line with the way you want the architecture to work? So it's multi-question. So,
yeah.
How is this different than a publisher
like a centralized pub sub? I mean,
that's what it
there's
looks
sub.
like.
There's a lot of subbing, subscribing.
Well,
and
it looks like you have a couple of publishers and a couple of subscribers, and so you have all these components subscribed to the individual events.
Yeah. Well, think of it in the Unix way. Like everything has both. It can take some kind of input and has one take one output, and outputs also. So everything is both a publisher and a subscriber. And so, not everything, but a lot of things are both publishers and subscribers. The scroll view would emit events 0 to 1, some kind of progress on how much have you scrolled, but its input is the mouse input. So the input looks very different from the output.
So do you get any deadlock on that because you have events dependent on events, which can end up being circuitous?
I mean, you can make a circular thing, certainly, just by listening to your own event. You don't even need 2 different things. You can just listen to yourself and create a circular loop that you'll never get out of. Yeah, but that's your fault. I mean,
thinking large applications like Team A doesn't know what Team B is doing, like 3 departments down, and so somehow you can always end up with like some sort of circular event if it gets too nested. But
yeah, that's certainly a problem. I mean, you don't solve those kinds of problems in this framework for sure. Yeah, sure.
Do you use request animation frame at any point in this, or is it just continually drawing?
So it's all backed by a request animation frame thing, which actually shuts off when nothing is happening. So that's the request animation itself is listening to what's happening on the screen. It will wake up when you touch something, set a stream in motion, and it'll turn itself off when the all streams emit an end event. When they're all at end, it turns itself off. There's actually a little bug right now that's not working, but it should work in the way that like when you're not interacting with the screen, literally no JavaScript is being executed at all. That's the goal.
So the idea of this to replace CSS where you're doing certain types of animations?
It's to replace the animation stuff inside of CSS. Yeah, but it's not supposed to replace color and like it's.
So you're still using CSS for your base things, is where you were doing some heavy animation. But where I get a little fuzzy here is that when you talk about responsive, that's generally baked into the Materialize or Bootstrap, and we're picking up that benefit from just using those.
Oh yeah, absolutely.
frameworks.
Yeah, yeah. So and you can this one you can still use all of that with this architecture, and it doesn't get in the way of that. Really, what I'd like to do with my responsive demos is to have like you'll see this guy. What I actually don't want is the binary change from a 2x3 to a 3x2 over there. I actually like that to be a continuous change. That's actually what I see with the future of responsive design. That's really what I see with the goal of this library is nothing is binary anymore, everything's continuous. So the next thing that I'll do with this example is you'll see the sizes animate and you'll see them translate with an animation to where they're supposed to be, which I think is the goal. Yeah, sure.
But technically, this stuff, if it were done in CSS, would technically be faster to get more kind of hardware acceleration, right? So on the one hand, it's more expressive, but on the other hand, it's technically slower.
There's only one thing that CSS can do that this will never be able to do, and it's to work on a separate thread. So only recently have browsers actually done their CSS animations on the UI thread and not on the CPU bound thread where the JavaScript is running. So that's the, yeah, it'll never be able to do that. But at the same time, you can never really stop a CSS animation midway. You can't, there's like so many limitations, but if for what you want to do, CSS will always be faster if you just have an animation running that's not interacting with anything on the site, if it's working in its own thread. So that's the drawback. It's unfortunate. Yeah. I talked to the browser and I was like, is there any way not to have this? Or to be able to do JavaScript on a separate thread also? Yeah.
Do you always get under, or do you hit 60 frames a second, or if you actually build something that destroys it?
Oh yeah, I think the tree demo is like 45 frames a second.
Okay.
So 255 elements, it's tough to get that. I couldn't go one more power, for sure. But it actually renders faster in JavaScript than it does in Canvas, or in DOM than it does in Canvas.
So let's just take one more question.
Since you already went, you can talk to me after. Okay. Yeah.
Oh, sure.
So I'll just go. Have you played with sockets to run streams from server side, and also have you tried thousands of downloads?
I mean, I've stress tested with the thousands, it'll just die. But with the but with the socket, it also actually depends how many pixels you're changing. It's not so much how many DOM elements, but there's like it's not. Yeah, it's more complicated. But with the socket stuff, I've never. So that would be really cool, especially for two people interacting with the page in itself. You can send the mouse events or some version of that. I haven't played. At Famous, we were playing with that in some other ways, and people were showing some like awesome demos, but I haven't done that myself.
Great.
Yeah.
Thank you. So we will all, I'm making assumptions for all of you, be going to a bar not so far away where you do not have to drink anything. I probably will not, because I will go and sleep at some point. But we will have opportunities to ask many more questions and dig in a lot deeper with all of the speakers. I myself, I should have tweeted that I think that the quote, "Oh well, with thousands they're all just dies," was really, I'm pretty happy out of this. So next up, we will have Alex Lee, if you want to come up here, talking about color. I think that this is a case where my usage of the title actually changed the name of the actual talk.
Well, no.
So feel free to use the real title.
Really, it's Mr. Giuseppe's fault.
That's true. Someone else did send me the title, and the title was sent to me incorrectly.
But it's okay. It got retconned, and now it's the real title.
Okay, great.
So the title's the same now.
I'm excited to hear Alex Lee about color and other things.
Wow. What is an revolution?
Just hit the record thing.
Yeah. Is there a
Scale.
where?
That's the second radio button down.
Down, further down a little.
Yeah.
Right, yeah.
Ah, okay. I mean, I guess everything just seems so small. Maybe I can. Is that better? That's good. right, so title is now Color, Math, and War, because of, as mentioned, Mr. Giuseppe has claimed that that is my title. Alternatively, how can colors be real if our eyes aren't real? So I don't know if you guys follow Jaden Smith on Twitter. He is an exceptional philosopher. He tweeted, "How can mirrors be real if our eyes aren't real?" Which, if you think about it, doesn't make any sense. Anyway, so this entire slide is made available thanks to Cloud9. It's pretty simple. So essentially, this is about color itself and how and why we represent color the way we do, right? So colors, you know from using CSS, you have the most basic version of it is you have RGB and you have 3 values for the RGB value, or you use a hash, right? So in using a hash, you're essentially doing the same thing as specifying an RGB value. But why 3 numbers? Like, why is color the way it is? So colors is an interesting thing. Color itself doesn't exist as a physical attribute. There's no intrinsic thing that is color. It is all perceived. So it is something that is created from your mind, from what you observe through your eyes, right? So color perception, on one hand, drives what color is, but there's still a lot that's shared between all of us. That's why we can still communicate about color, and it's not just like everybody fighting about what green means, except for this one, right? So if you still remember this still looks, actually it swaps on me every once in a while. This is a case where colors, due to the way we understand the context of the light being seen, will change on people. So color perception is dependent not only on your own physiology, but also the framing of the whole thing. So this picture seen in different contexts, like if you imagine it to be seen from a dark room into a light room versus the other way around, will change your perception of what that color is. So there's a lot of things that are dependent on your psychology at that point of time, but there's also a lot of shared things, right? So we all have eyes, hopefully. Our eyeballs are constructed with cones and rods, we all know that, right? So the color receptive things are called cones because they look like cones when you put them in a microscope. And we have 3 different types of in our eyes, and they have different frequency response ranges. So for different light frequencies, different neurons fire. And they are receptive to different frequencies across the visible spectrum. And it's due to that we're able to distinguish any color at all. So without having multiples of these, we can really just tell whether or not something is light or dark. But since we have multiples, humans are mostly trichromatic, which means we have 3 color receptors. There is a genetic mutation on a small percentage of women who actually are tetrachromatic, which means they have 4 color receptors. So you'll find some of these things in nature as well. There are tetrachromats in nature, like certain birds. So there is a bird, the European starling, which looks like this guy. This guy is a tetrachromat, has 4 different color receptors. So you can see in the graph here the comparison of how much color we have actual response to versus how much color they have response to. So to these birds, the frequencies that we see as somewhere in between blue and green, that teal range, is a completely different color. It's a different sensation for them, in fact. So if you have I don't know what that disorder is called, but if you have 4 chromatic receptors in your eyes, you will experience the same colors very differently from the rest of us, the vast majority of us. Interestingly enough, the frequency response is also responsible for color blindness. So how many of you are colorblind? Red, green? red-green color blindness. So red-green color blindness results because if you see, this is the red cone and this is the green cone. They're very close together. They have a lot of overlap. Red-green color blindness happens when the genetic mutation causes the frequency responses to shift so that they overlap even more until very little is capable of differentiating what is green versus what is red. So there are glasses out there that try to correct for this by essentially cutting out the middle band right here. They filter out the middle band right here so that you're trying to hit the edges of these receptive areas so that you can focus on red versus green in order to separate them. So, and then there's other different types of color blindness, but it's essentially the same idea. You have 3 different color receptors, and however much they stimulate, they are stimulated is however you perceive those colors. Now, what's the next slide? The RGB color space. So going back a bit, it is because we have these 3 frequency response ranges that you'll note that we have red, green, and blue as our primary colors. Because sometime during like the 60s or 70s, some researchers were essentially just like going around showing people slides of colors, and trying to figure out what differentiated colors the most to people. And it turns out it was these colors, and they came up with a coordinate system. And they called it RGB because it was red, green, and blue. So you have the RGB color space, and this is a color cube. The color cube is created from you see that bottom left corner is black, that is the absence of all color, absence of all light. And so as you add light, as you add red in that direction, it becomes more red. If you add green, you go up and it becomes more green. And if you turn it the other way, blue is the 3rd axis. So in controlling these 3 colors, red, green, and blue as 3 independent axes, you have control of pretty much how much of each of the type of cones gets stimulated. And the degree to which those things get stimulated controls how you perceive the color. So that's why we only have monitors with RGB and I guess like white or black. But mostly the pixels, if you look very closely, the pixels are created out of 3 different colors, RG and B. That's all you need because we are, as far as I can see, all humans, and we see colors pretty much the same way with just red, green, and blue. But if we wanted to create a monitor for the Starling, the European Starling, we would have to create monitors with 4 different types of light. There are also, interestingly enough, animals that are on the far end of the spectrum with 20 color receptors. And this is the mantis shrimp, this guy. This guy has 20 color receptors, so if you want to make a monitor for him, he will require 20 different colors in every single pixel. Fortunately, he's not near the surface, so we don't have to make any screens for them. Yet. But in order to represent all the colors that they can perceive, we would need a color space that has 20 dimensions. We would need a 20-dimensional cube. Fortunately, we only need 3. That is the most basic color scheme that we can have is RGB. So RGB is pretty great. You can see all the major axes here, and when they blend, they make these other nice colors on the other side. Let's see if I can get this cube this way. RGB is pretty great because you can represent pretty much all the colors that humans normally deal with. There are certain colors that are not representable, but we'll get into that later. But that's not how humans think about color. So there's a problem here. If I say that I wanted seafoam green, how many of you can tell me how much red that requires? None of you. Really? It's 118, come on. That's the problem, is that humans don't think about colors in that way. We don't think about it as a combination of how much our photoreceptors are actually getting stimulated. So it's a very unnatural thing for humans to deal with, a very unnatural thing for humans to think about. So some researchers back in late 70s, I think like 79 or something, they went about to try to create a color space that is more natural to humans. So as humans, we see light and darkness most of all. And then colors are kind of like nice things that you get on the side. So what they did was they took this cube and essentially just stood it on one end with black at the bottom, white at the top, and said, well, we're going to try to create a color space based on that. Because we know that from the cube we can represent all the visible colors, but if we do it this way, we'll have the nice gradation of brightness versus darkness that most of us understand, and then color becomes just another aspect, right? So this is what they did. They took the RGB cube, they rotated it so that there's black at the bottom, white at the top, and then because in order for the math to work out like this cube, you would have to go through some pretty heinous math. They normalized it. They essentially merged all the colors together, so in the middle it becomes a wheel, a circular wheel of all the representable hues. The definition of hue is essentially what we think of as actual color. And then as you go up or down, it becomes closer, like more and more bright and more dark. And as you enter, as you go toward the center of it, it loses its, it's called chromesticity, but essentially it becomes more desaturated. So what you have is this color cylinder. The cylinder at the bottom is still black, at the top is white. Around the middle is where you have the most saturated colors. As you go inward, it becomes more desaturated, more gray. So you can represent the same colors as in RGB space, but this time in a radial format. So you can go from red and then just circle around and maintain the same relative lightness, brightness. And that is what HSL does for us. And that turns it into this thing. So you have saturation. It's essentially how vivid a color looks. Lightness is how bright. And then hue is which color it is, right? So with this, now we're able to take the same thing as the RGB color space, the same number of colors, and then represent it in a manner that is more natural to humans, right? So you also notice that in the HSL color space, if you go to full white or full black, it doesn't matter which hue you're on or how much saturation you have, because at those points, it becomes the single color. This is a trade-off. This is a trade-off that you're gonna have to make in order to get a coordinate system that looks like this. So the thing about coordinate systems is that they can't restrict you according to like what makes sense in the color, because you can't represent it as the color cone that it actually is, then because the math gets real heinous, and then you have to run into these kinds of things, and then you don't want to do any of that. So in order to represent that, you make the compromise of saying if you go full white, you're going to be all white. You go full black, it'll be all black. But it's in the middle that's where most of your color comes from. So from that, you can tell when the design, I don't know how many of you have had to make a color picker, but we've had designers try to design color pickers that don't make any sense because they don't allow you 3 degrees of freedom. You always need the 3 degrees of freedom in order to represent the number of colors that we can see. Even in HSL, you require hue, saturation, and lightness. In RGB, obviously, it's RGB. So with 3 axes, you need 3 inputs. Anywhere that you have a color picker that doesn't have at least 3 inputs, They're lying to you and they're making you pick palettes, which is not the same thing. So how many of you remember in like Windows 95 or something, you have to choose between like true color or like 256 web colors? 256 web colors is a palette color scheme, which means all the colors in there are pre-picked by humans in order to be represented. So what happened is in like 90s or something, true color came about when Microsoft decided, okay, we need one way to represent every color we can see. So they took RGB, they split the axis into 256 data points. They split each axis 256 data points. And for 256, you need, is it 2 bytes to represent it? Or 2 bits?
Bytes.
Bits, bytes, I don't remember anymore. 8, right? Yes.
8 bits.
Yeah, 8 bits. So you need 3 of those to represent the 3 colors. You need R, G, and B. So 3 times 8 is 24. You need 24 bits. You need 24 bits to represent this color. And that is how you got to RGB space being represented from 0 to 255 in 3 different axes. And so when you go into CSS and you say RGB and you open parentheses, close parentheses, in the middle you have 3 numbers, that's where that comes from, mostly because of Microsoft. But you can also choose to have HSL, in which you don't specify how much light you're giving out. You're specifying which color, how much saturation, how much lightness. So with that, you're able to make colors that make sense to you, right? And let's see how much. Yes. Now I talked about coordinate systems for colors. Now the thing with coordinate systems is that they're just math coordinates, so you can do whatever the hell you want with them. There are such things as impossible colors, colors that are not representable, or colors that are representable but not actually displayable. For example, you can, in the coordinate system, you can totally have negative numbers. So if you ever think about what a negative red looks like, that's where you get into the impossible colors. So there are some colors that are mathematically possible, not realistically possible. So like negative red is a good example. That's mathematically possible to represent. It is not a real color. It is not something that you can actually get your eyes to do. And then there are others that you can actually get to, but not under normal circumstances. Those are called chimerical colors. And Jean-Paul, can we turn the lights off or down here? Because I have a demo for this. Let's see if I can actually. So here is going to be a chimerical color. The chimerical color is going to be called, it's called Stygian blue, named after the river Styx. So what you're supposed to do is just stare at that yellow dot for a minute, right? Don't move your eyes, stare at the yellow dot until you go crazy. Stare at the yellow dot, and then the screen will turn black, and you will see the Stygian blue. Stygian blue is named after the river Styx, which is described as being as blue as it is black. So what this does is it fatigues out your color receptors for red and green by showing you yellow. And by fatiguing you out, when it flips to black, suddenly your brain will compensate the other way and make you see blue. And I don't know how long a minute is, but keep staring. I swear to God, it's not like a scare.
Let's go and see.
Come on, it's Rickroll.
I hope not. Then I would have rickrolled myself a lot of times. Oh, there it is. You see that blue dot? You can move your eyes around on the black and you will see that blue dot follow. It is not a trick, I'm not doing anything special, it's just black. It is just black. That is Stygian blue. That is what happens when I fatigue your photoreceptors to the point where your brain says, okay, this can't possibly be that color. I'm going to compensate the other way, and then forces the blue receptors to say, no, that's totally blue.
And there's no way to represent that?
There's no way to represent that because it has to do with, well, I mean, technically you can as a negative green and negative red.
well, mathematically, but I mean, there's no way you could generate that color.
You can't force people to see that, no. Not without doing what I did, which is to force you to look at the yellow dot for a minute.
But you can actually like paint that color.
No.
What do you mean?
You can't.
You just said negative, so if it's conical coordinates, it's just the opposite direction. It's a what's the term for it? It's
Here's the thing. You can't have negative light. That is the primary thing. You can't negatively stimulate your neurons. That doesn't work. Your neurons either are active, like there's degrees of activity, but there's no negative activity for neurons, right? So you can't at once force the neurons to become negative. What you can do is to trick the thing that's interpreting the neurons to say, this feels like it should be the other way around. And that's what the fatigue does, is to trick the thing that's interpreting all the things coming from your eyes into saying, no, this is not black. This is something blacker than black. And that's the sticky include. So that's all oh right, one last thing is, that's fine. That's all I have for colors. This is, what? Oh, no, it's just the color picker that we have, right? So this is the color picker that we built at Behance for portfolio site. And you can pick the color as a hue on the hue wheel. This changes, this is, the wheel, the round portion of the HSL color space. You have saturation, so that if you desaturate it, it becomes more gray. And then you have lightness, which if you drag all the way up, becomes white, and then it becomes black at the other end. So with that, you can represent any color that you can actually see. So that's our color picking.
Just a critique of this, you're showing an RGB value, but it's actually to represent an HSV value. Don't you think there'd be some value in showing the HSV value as well?
No, because there's a direct mathematical relationship between an RGB value and HSL value. Technically, you are right, because at the extremes, when you have white and black, I can't actually make up a hue value and a saturation value for this. Because at the extremes, white is white, black is black, and that's the compromise we made for HSL. So if you are at white, like if you put in all F's here, I don't know where the hue is, so I have to just guess, right? I don't know where the saturation is either, so I just guess at that as well. And you can see the slider has moved all the way to 0. And if
you mean it just doesn't matter?
Yeah, it doesn't matter.
You can guess what you want, it doesn't matter.
Right.
Okay.
Like I can actually drag the thing around and it doesn't change the color any. You won't be able to change the color until you have some sort of differentiation in saturation or lightness.
Do you know the equation between HSL and RGB? It's really interesting.
Yeah, it's a 6-way stepwise function, because what they're doing is they're doing a interpolation between every single angle in the color cube. So if I go back to that color cube, where's that cube? So if we look at it from top on, right on here, you see there's 6 different corners that you can get to. Essentially, they're taking those corners as the absolute, as anchors around the wheel, and they're doing interpolation between every single anchor. So it's a 6-way stepwise function. And I think that is it for me. We are hiring at Behance, by the way. If you want to get hired, talk to Giuseppe. He is one of the people empowered to do that.
To talk about working at Behance?
To talk to about working at Behance.
You know, I talked to you.
No, I know. I'm just surprised I cannot talk to Al.
I mean, you can talk to me too, but I can't do anything about it. I can tell you all about the colors.
A lot of colors at Behance.
It's a thing. Okay. Okay, so if there are further questions, again, I'll give the details, I suppose, right now. If there are further questions, you can talk to Alex, David, and Nathaniel, I'll be introducing in a second, at the Hog Pit. So we are going to go, it's a great name. It's called the Hog Pit. And they do have very good pork, although I've not had it in a long time. Their specialty is something called a pickleback, which I find quite disgusting. Some people enjoy this. It's pickle juice and tequila. Have you heard of that? Oh, it's whiskey? That's even worse. Pickle juice, you could have given me the tequila thing. It's roughly like 3 blocks that way, and it's going to be a very straightforward walk. We'll be going from here. So, I'll introduce our last and final speaker in a second. I want to take this time to thank Autodesk, which are very graciously giving us this space, the food, the cookies, which I don't know if everyone's eaten, so it's been basically just me. You should stop and continue to eat them. And the sodas, as well as this beautiful space, electricity, heat, and all of the other things. So they do lots of very interesting things. They have some great, interesting WebGL demos and now developer tooling that if you're interested in, I would love for you to talk to me about. Talk to Jamie in the back. We have lots of, they're continuing to support us here at NYCHTML5, as well as I'm trying to learn more about WebGL because, first of all, there's some demos here. I find it very interesting. I got a free O'Reilly book that's like tiny, but extremely complicated about WebGL recently. So I started reading that and hadn't realized I had no idea what I'm doing, and I need to use an API like Autodesk will provide. So in terms of the next meetup, I'll talk about that after our last speaker. So there will be some planning, and I would like to get some help if there's anyone out there who would like to volunteer for these kinds of things. But lastly, in terms of our speakers, I'd like to bring up Nathaniel Lee, who will talk to us about React experiences at Nexus.
The title of my talk tonight is Reacting, Simplifying User Interface Code at Nexus. It's going to be a shorter talk than the ones that we've had, so we can get out and get to drinking. So I'm going to give kind of like just a really brief, general, high-level overview on some of the challenges we were facing in our user interface code at Nexus, why our team felt that React was the right solution for us, and some steps we took, some things that we did to start bringing React into our stack. So here's a obligatory About Me screen. This is an About Me React component. My name is Nathaniel Lee, as John said, and I'm a software engineer on the buy-side forecast and order entry team at Nexus. So let's talk a little bit about code complexity. So imagine for a second that you're a project manager and you're in charge of a really large project. So perhaps building a new application on your platform. And you're gonna have a lot of different teams working for you, front-end team, back-end team, data team maybe, UX, docs, hopefully you have a QA team. Not all companies budget for that, but yeah, hopefully you have one of those. And imagine further that each of these teams is broken out into sub-teams. So some of these teams are going to focus on particular screens or particular sets of screens in your application, focus on maybe feature sets. And then imagine you're doing this without any project management software. Right? So no Jira, no Redmine, no Basecamp, no Pivotal Tracker, nothing like that. So instead, when your stakeholder comes to you and asks, how's the project going? You've now got to go to each of your team leads and ask them, how's the project going? And then they've got to go to each of their team leads and ask, how's the project going? And they've got to go to each of their team members and ask, how's the project going? Right? It's not a great setup. And this hypothetical scenario is unfortunately pretty analogous to how our user interface code was built at AppNexus. We work on an application called Console, which is a user interface that communicates with the AppNexus API. It basically on each page, when it loads, it hits the API, pulls down a whole bunch of data from the API, which basically represents the entire state for the app, for that page of the app, and then pipes that into modules, various modules, and those further break the state out into submodules and submodules and submodules and submodules. And so you get this situation where you have all this state distributed. There's no real way for you to tell what's going on at any given point in time, what the state of your application is. I'll switch really quickly, let's see, to show some examples of code. Let's see, so this is one of our modules. It's a segment grouper. Don't worry too much about what specifically is going on, but this is, actually no, this is the wrong one.
You increase the font.
Yeah. This is increase this font a little bit. Is that better or a little bit better?
Go for full screen.
Alright.
The string builder?
Yeah, basically. So when this when this particular module loads up, it basically gives you this initial state. So you know what the initial markup looks like. You know what the initial structure of the DOM for this particular module, mind you, looks like. But it's only that initial state, right? So if we go a little bit further down this page, now we have a whole bunch of jQuery calls to grab specific pieces of those of that markup and assign them to variables. And then later on, further down, we're going to mutate those, mutate the values in those variables, and then listen to events that are firing off of these components. And to go in there and try to figure out, let's say the user's done a certain number of things, the application is in a particular state. There's no way to really kind of figure out what the UI is going to look like given that state, and also at any given point, you don't know, to try to find and trace the state in something like this is just kind of a nightmare. And so we started trying to figure out, was there a better approach to the way we were doing things? We started investigating various solutions out there. Obviously, we're looking at things like Angular, Ember. We actually even have teams, a couple of teams in other parts of AppNexus that use those frameworks already. But the challenge with using these kind of solutions was that they're frameworks. They're heavy frameworks. They're opinionated. They lock the engineer down into a particular way of building your application, of architecting your application. And we really just wanted a way to kind of separate that code that handled the state of the application and the logic around that state from the view rendering code, right? The code that determined what the interface should look like at any given point in time. There was really no reason for those two aspects of the application to be so tightly coupled together. So a number of engineers started looking independently. It wasn't like any sort of top-down decree by management to say, start looking at React. Right? A number of us started independently looking at React, and we were kind of drawn in by a lot of the buzzwords that you hear around all the hype. But each of us kind of came to the same conclusion that React was the right solution for us, and that was for a number of reasons. The first one being virtual DOM. Yeah, it's a buzzword. I know John hates when we bring that up in React talks here. And also, yes, it's not really exclusive to React anymore. It never really was exclusive, but there are a lot more frameworks that are starting to leverage this concept of a virtual DOM. But it's still the key ingredient in why React is able to allow us to design our components the way that we do, design our render methods such that they can be a little bit more declarative in nature, and instead of having to imperatively determine, what part of this markup, what part of this DOM that I'm producing needs to be updated on a state change. We basically just describe exactly how the state should look given any set of data, and then we kind of toss it over the wall to React and say, hey, virtual DOM, you decide how, you determine how you're actually going to affect that change to the DOM. And then there's this concept of unidirectional data flow. Probably kind of another buzzword around React. We were talking before about frameworks. A lot of them use this concept of data binding, right? So you have the model, and the view is listening to the model to see what, anytime the model changes, the view will update, and then at the same time, in a lot of these frameworks, anytime the view changes, the model also then is listening to it and changing itself based on that. So the data is kind of flowing freely in both directions. And React instead favors this concept of a unidirectional data flow, this architecture where the data flows in just one direction, right? The props go into a component. The component then renders a view, right, what it thinks the view is going to be based on that state. And then when the user triggers an event on that view, the component passes along some pertinent piece of information about that event. That gets passed back up to the model, and the model then determines on its own how state should change based on that event and that data. And the cycle repeats itself. It gets passed right back down to the component, which re-renders itself, and so on and so forth. And in fact, if you don't pass any sort of event handling functions into a component, like let's say you have a checkbox and you don't tell it what it should do when you click on the checkbox, it won't actually do anything. So if it's started out in a check state, you click on it, it won't actually ever leave the check state. It will always be re-rendered over and over again as checked. There's a streamlined API to React. So one of our main problems, like I said, is that we didn't really have, one of the main problems I didn't say was that we didn't have any sort of standards around how an interface with AppNext's module should be defined. Granted, we can normalize on some sort of code standard, but nevertheless, with all this kind of state that we're passing in and out of these modules, a developer would have to anticipate an interface that's a lot more complex than just a simple get set pair, right? For every piece of state that might go in and out, we have to have some sort of get set pair just for that piece of state. And by contrast, React offers a very simple, straightforward, and streamlined API. You're never getting or setting anything, and the minimum you even need to define on a React component is just a render method. So let's see if I can take a look at render method. So let's go to here. So if you look here, we have a component here. It takes in a bunch of props. There you can define default props on it, and all the props are always on this.props inside a render method. And so you basically define this markup, and it's not really markup. It's actually a syntax they call JSX that React that can be transpiled back to pure JavaScript. And you basically see this entire, this is the entire markup for this particular component, right? It's not only just the initial state, it's any possible state that this component can be in. How it defines right here how that view is going to look based on that state. And really, actually, all you need for a component, I mean, this is a more complex component, but you can get rid of all the other stuff up there, and really all you need is to define a render method on the component. That's the only required method for a React component class. Another attribute, I guess another quality of React is that it's quote-unquote functional. Components are objects in the sense you're creating classes, but they pretty much just boil down to this concept of a pure render function, right? The result of defining a component is actually a JavaScript function that takes in data, like I said, and returns a description of the view based on that data, and it's consistent, right? It's this power consistency that comes with the functional approach. No matter what, if you pass in a particular piece of state, a particular piece of data in a particular state, it's always going to bring you back to, it's always going to spit back the same view over and over again. Right? There's no having to, well, you could put state in components, but it's generally considered bad practice. It's just JavaScript, right? If you go with a templating solution, you're gonna you have to learn maybe some sort of custom syntax around how you iterate over data, right? Maybe instead of a regular for each, you gotta kind of learn how their each iteration works. But with JavaScript, the JSX syntax aside, and like I said, that just gets transpiled a bit into real JavaScript. You're really just using JavaScript. So, you know, if you have an array that you're passing in, you can just latch onto the native method, you know, each method or a map method or whatever you want. Or if you prefer, you can leverage something like underscore or Lodash, one of their methods. But, oops, sorry. But React isn't really opinionated about how you do it. It's all just JavaScript. And I guess finally, another key thing for us was that you can really just try it. Like I said, React isn't a heavy framework, so with Angular and Ember, you kind of have to change the way your application is structured. Right? You gotta change the entire page, how everything is architected. Whereas with React, you can literally just kind of pop it into a small piece on your page in your application, and you don't have to worry about rewriting your entire code on that screen. You just need to worry about that one little piece. And I have an example, if I can find it, here of, let's see, here. So the rest of this page is actually, well, this is one component that we have that is, you know, basically just pulling in a couple of our React components, and then this component is actually pulled in by. I must have lost it. Sorry, I must have lost the file. Well, basically, it's just pulled in by. In this case, it's the React is imported in here, and then right here, in this file, in this module, I return out a function which just takes in any old DOM node, and then React renders this component onto that DOM node. So for any consuming code that uses this module, what it's going to see is, you know, what's the C being returned back out is just a function, and then you pass in wherever you want to mount it, and you know it mounts it on its own, and then it handles its own state and handles the property. It handles all the props and handles all the events and everything. So your consuming code doesn't even actually even have to know that it's React. All it knows is that it's passing a container node into a function, and then you know the component is taking care of rendering the view map. So some steps that we took. This is the last part of my talk. Some steps that we took in integrating React and kind of getting the company to adopt it and getting other engineers to adopt it in our company. The first one was a shared component library. This is probably the most important thing that our team did. And when I say our team, I actually mean our team out in Portland. They were a little bit ahead of the curve compared to us in New York. But they basically came up with this idea of creating a shared component library, a shared library of React components that can be used across the application. Our existing framework right now, one of the good features that we have is a component library, but it's a component library with all sorts of state, like the code I showed you before, just state everywhere, and it's really difficult to kind of move through and reason about. You're hopping through lots of different files to try to figure out each little piece of the state. Whereas in this case, we have a library of shared components, almost all of which are very pure. So you're basically just passing props in. Most of them have no state whatsoever inside them. And they're just really basic things like a button or a drop down. We have a few more complex interface patterns that we just took a bunch of these base components and composed them into more complex interfaces. But again, in the end, it's this shared component library that we can, anyone, even people that aren't on the console platform like we are, people that are using Angular, or people that are using Ember can actually, hit our private NPM repository and pull this package down and just start putting React components into their interfaces. And this is, we treat this like any other open source project. So we use a semantic versioning system. We've established contribution guidelines so that other people, anyone can pretty much just come in and just start contributing to the library. We have a clean change log that gets updated with each version, that gets pushed out. We have weekly meetings. agenda items that we determine before the meeting. We record minutes, and we actually have video conferencing for remote contributors because, like I said, we have people on both coasts. We have people in California, in Portland, here in New York. So, we have a lot of people contributing to this library, and we actually have hosted examples. You can basically, when you write your code, there's a really easy interface to create these examples, and they get automatically deployed to a dev server that can be linked in pull requests. And I'll show an example of that here. Yeah, so actually, when you first, let's say you branch off of Annex React Master, and you make your changes, you push them out. What will happen is it will actually publish to this server here, and all along here, are just these are all the different branches that people have out there. And so you can click into any one of these. Right now, it's probably gonna be a little bit slow going in, but you can click into any one of these, and you'll essentially see this, which is the component gallery. And it's actually also just React components. We built the gallery out of React components, so this entire page is React. We have a lot of components all on the side, and yeah, see tons of components here. You can click on any one. You can click on ones to get individual components, and they show like the actual little examples. Like this is one that's checked, and this is the default version. Here it is disabled, and you can click on here, show source, and it'll actually show you this little kind of mini example component and what kind of props you have to pass into that particular component to get it to render out into that state. So yeah, it's quite useful. One of the cool things is that you like I said, you publish this out, and then when you create a pull request for your component, you can actually link to specific examples, and that way, someone instead of just going in and seeing a whole bunch of code that's changed, and they can actually go to this and see the results of those changes, and verify that actually works the way it's supposed to. And you have simple ones like checkbox, but like I said, there's also some more complex ones, right? So this is actually a composite out of buttons and a button group. Each of these icons is its own component. This search search input field is a component that's actually a text input with this little search icon. This, I believe, is a component as well, header, and then the grid is a component, and a grid is actually a composite itself. We have headers, we have columns, we have rows. Down here we have a paginator that's composed of drop downs and buttons and a text input. So one of the beautiful things about React is that you kind of you build these little components and then you compose them together into bigger components. You compose them together into bigger components. And even this one right here, this component right here, it's fairly complex. It's not that complex, but it is still fairly complex. It's not just a button or a checkbox. And it's also completely pure. So there's no state going on here. All of these are just props that are going up and down. You pass in the props, you pass in like what the data is. Each of those pieces of data gets passed into subcomponents. And then when someone does something, like let's say, I don't know, I'm not sure if this one is set up to work. Let's say, click that, yeah, click that, and then event comes out, and then the consumer can then handle that event any way they want. So the consumer has his own model. It's going to update that particular row is selected, and that gets passed back down into the component, and it re-renders itself, and it shows you the updated selected row. So yeah, that's basically it. On that, here's my segment chooser. So before I was talking about that segment chooser we had, this is a React component version of it. And again, it's composed of lots of different subcomponents, which themselves may be composed of lots of different subcomponents. We're basically just passing in a blob of data state that describes what segments are available to choose from, what segments have already been chosen on the right side, whether they're included or excluded, because that's part of how we deal with segments in our platform, what the name and the values of those segments are, and you can create new groups. So if I've dragged one of these in here, it'll create a new group. And now when that's happened, it passes back up. It says, hey, new group, update the state to reflect that. and that gets passed back in, and so on and so forth. So that's kind of that unidirectional data flow for React. Let's see, and I guess that is, yeah, so I guess another thing that we had to deal with was flux architecture, right? So, like I said, part of the promise of React is this unidirectional data flow. And the Facebook team also introduced another concept, what they call the flux architecture, which is, I guess it is kind of opinion. It's an opinion on how developers might architect their model and how they would design how the model relates to the view components. Right? And it's not really an actual technology. It's just a concept, an idea of how data should flow through the system. And we started off creating an implementation of that we call ANX Store, which is really just a wrapper around open source library called Baobab. It's just a state management library. But now Redux, I think, is, we originally investigated Redux as a possible solution, but it wasn't really fully baked enough at the time. So we went with this custom solution. But now, I think the most recent releases are pretty well baked. They're pretty much what we wanted in the first place, and the community seems to be kind of converging on Redux as the de facto standard for Flux style state management. So we're moving in that direction as well. And another thing that we needed to take care of was transpilation step in our build. So if you want to really, use React, really get this declarative expressive power in React, you need to be able to use the JS6 syntax, and that's something that you can't just pop into a browser. It needs to be transpiled into quote-unquote real JavaScript. And so we have like a kind of internally in-house, homegrown module manager system, and that there's no way to get a Babel transpilation or any sort of transpilation into that. So we started investigating ways to transform that, to replace that really kind of heavy opinionated module manager that we have, unfortunately. Replace it with Webpack, which is kind of this modern module bundling tool that's available. It's been gaining a lot of steam, especially with React, because it's one of the best solutions out there for including Babel transpilation. And and Babel itself is important because originally React provided their own custom kind of JSX transpiler, but not too long ago, a few months ago, the React team themselves deprecated that in favor of actually just officially supporting Babel as the official transpilation partner of React. So it was kind of fortuitous that we went with Webpack. And finally, a few challenges. So one of the big challenges we have is that console is this really big monolithic code base, right? We can't just we have a lot of live customers on it right now. It's a big code base. A lot of people are using it, and we have lots of real money transacting through it. So it's not something where we can just say, all right, we're going to go and replace every single page with Webpack. There's a lot of steps. There's a lot of kind of effort we have to put into it. So most of our application actually is not ready for React, unfortunately. But in a lot of cases, we want to still be able to use, to leverage React to use even just basic ES6 transpilation. So before I was showing this, is this the other one? Yeah, so this integrated component, right? So this is using JSX down here, but the page on which this resides is not Webpackified. And so one of the solutions in this case, the solution we have to go with was this kind of hacky adding a grunt or a gulp external script that would run Babel and transpile this file. And then we end up with two files. We have this original JSX file, and plus we also have the compiled JS file. And we have to actually check both of those into our code base, which is not an ideal solution. Actually, our core kind of console architecture team has decreed that we should stop doing this.
Good luck.
Yeah. And the other approach was actually the team that built ANX React originally. Before they did ANX React, what they were doing was just doing the pure JavaScript version. So let's see if I can find what the pure JavaScript version of React looks like. Let's see, shared React. Oh, here, shared React. So here's like a button, let's say. So here's the render. So there's no JSX here. This you can just pop right into any page and it's going to work. You don't need any translation, no kind of battle step or anything like that. It's not quite as sexy as JSX. It's not as representative and not as expressive, right? With JSX, you would say, oh, return a button. That's and it looks like markup. It looks pretty much like what you would expect your HTML to look like. Here instead, you're basically just calling the generic button method in React.dom. And that's just, they provide a set of methods on React.dom that map to pretty much any valid HTML element. And you pass in props in this format, this object literal. And then you pass in, on the last step down here, you pass in whatever children you want to use it. And then you create a factor out of that and you return that. You basically return that out. And then any code at all without having to use React whatsoever, or just take this button, use the factor, and insert React buttons onto the page. So that's the other step. I guess that's preferable. I mean, I would rather just go into JSX and then do the hack. When I'm touching those pages, I'm still using that hack on those few pages that I've worked on. But like I said, our kind of leadership team has mandated that we never do that for anything new. So now we basically kind of focused on anytime we want to, if we really want to use React that badly on the page, then we got to go through the steps of replacing the module bundler on that page with Webpack, and therefore then we would have the translation step and we'd be able to leverage that. Otherwise, we have to either go with pure JavaScript or just go back to doing things the way they were before, which of course not great, but it's a slow process. Unfortunately, we have a really big code base, like I said, and this has been a few months that we've been doing this, but I wish I could say it was like a really fast kind of, oh yeah, overnight or over a week we were able to do this, but because it's a big application, we have hundreds and hundreds of modules in here, we really have to kind of take our time and do it a little bit slowly. And like I said, there wasn't any sort of top-down decree. There was no official support for adopting React on our stack. It was kind of a grassroots efforts on the part of engineers who really just wanted a better way to do things. We didn't want to have to keep dealing with all the state the way it was, and we kind of just found React as the right solution going forward. And on our own time, 20% time, weekends, nights, kind of put together this library. We put together, we started transforming these components to kind of try to convince product management, convince the rest of the team, advocate to other engineers that this was the right way to go, and to kind of, in the beginning, hand-holding a little with some people and having classes. My colleague who's here tonight, he and another colleague of mine actually organized a 10-week session, a 10-week, course of weekly lunch and learns, so that anyone interested in learning React as a team can kind of get in. They would order lunch and they would just go through various exercises to learn different aspects of the language, how to use React, what Flux architecture was, maybe how to use Redux, things like that. So basically just kind of acclimating everyone to doing that. And it's really this kind of like evangelizing, almost like we were trying to get open source project more support. Have to go to all the different engineers and kind of tell each one individually or hopefully as a group, just these are the reasons why React is good. Here's an example of what you can do and why it's better than the way we're doing it now. Let's work through some examples, over lunch. And so kind of just generating interest, generating support in that fashion. Hopefully, if you guys ever go and start going down the React route, you'll have a little bit better time, maybe you'll have more official support. I'm sure it's a lot easier and a lot better when you have official support. Now we have it, but like I said, it's a big application, so it's probably going to be a few more months, if not longer than that, to even start to see like a real like significant shift in the portion of the application that's using React. But I think it's time well spent. It'll be time well invested, and the end result will be a better code base for all of us to work on. And that's really all we wanted in the first place. That was all we were looking for. So that's basically kind of what our path towards React. We're still far from the finish line, but that's what our path towards a React code base has been like. That's all. Thanks.
So if there is a question take one. And then
Yes. Have you looked at the System.js versus Webpack?
System.js? No. What is that? Oh, instead of Webpack. Oh no, I mean Webpack. We were actually kind of converging on Webpack before we even looked at React, because like I said, we had this big monolithic code base, so we needed to get out of having this giant code base. So we wanted to go with the open source tool that would allow us to kind of bundle our modules in a different way and allow us to kind of start integrating these different translation steps or other build steps. You know, if we wanted to change the way we were linting code or change the way we were testing code, we wanted to be able to do that. And Webpack was kind of gaining momentum at the time, and most engineers just kind of went with that because they felt like that was a better solution to browser find.
Okay, so I will be very quick. The next, so I hope to see you all at the Hog Pit, understandably. It's kind of late, so I expect some people to drop off. But if not, we will see you down the street very soon. If any of you, I know that tons of people in this room are excited about the things that they work on. I am consistently looking for new speakers to fill out my schedule for next year. If you are interested in speaking, please let me know. I will find time to schedule. I will work with you to make your slides. We can make all of this work. Let me know if you're interested in something, if you're excited about something. I know that you can come up here and speak about it. So let me know. Thank you so much to all of the speakers. It's a hell of a lot of work to make these presentations, and I really, really appreciate all of the work. Thank you to Autodesk, the sponsor for our venue. Thank you all for coming. Have a good night. I will see you all hopefully at the bar. You don't have to drink anything. I won't be. Or next.
I'll reach out to you. I've been